Hello mathophiles. On this adventure in algebra we're going to discuss some examples of the first isomorphism theorem. Alright, let phi be the homomorphism from the integers, which remember this is a group under addition. To the abelian group C mod 2 pi z, be given by the map that sends phi of x to the equivalence class of 2 pi x. Now remember, this is an equivalence class, so it's all things of the form y, where y minus 2 pi x is equal to an integer times 2 pi. In other words, all angles that are coterminal with 2 pi x. It is not hard to see that this is a homomorphism. Two pi x plus y. Phi of x plus y, where x and y. Oh, these shouldn't be the integers. This should be the real numbers. Sorry. Let me fix that real quick. Phi of x plus y is the equivalence class of 2 pi up times x plus y. Multiplication is distributive. The equivalence class of the sum is the sum of the equivalence classes. And so we get phi of x plus phi of y. So this is a homomorphism. So by the first isomorphism theorem, R mod the kernel of this homomorphism is isomorphic to the image. Well, what is the image? What could we get as a possible set here? Well, I claim this map is surjective so that the image is everything. Well, how do I show that? Well, you need to take an equivalence class. And you need something to map to it. So take an equivalence class. By definition, it must be an equivalence class. Y is equal to square bracket c for some z and r. What do we need z? We need z to be of the form 2 pi times x. So, thought bubble. We need z to be equal to 2 pi times x for some x, because then it's equal to that phi of x. So what x should we pick? We'll divide both sides by 2 pi. And we see x should be chosen to be z over 2 pi. So let's try that choice. Phi of z over 2 pi is the equivalence class of 2 pi times z over 2 pi. We get cancellation and we get z. We get y. So congratulations, this is surjective. Now let's figure out what the kernel is. The kernel is going to be all those elements for which 2 pi x is the same as the equivalence class of 0. Remember, that means, by definition of equivalence classes, that 2 pi x is in the equivalence class of 0. Which means that 2 pi x must be equal to an integer times 2 pi. Well, if you cancel out the 2 pi's, you see that x must be an integer. So the kernel's the integers. So from the first isomorphism theorem, we see that R mod z is isomorphic to R mod 2 pi z. This group is kind of easy to understand, or at least it's easy to understand the equivalence classes. All you need to do, for instance, is take any real number, take its decimal expansion. For instance, with e is equal to 2.718 dot dot dot. Well, a good coset representative is to just get rid of the part before the decimal. This gives you a number between 0 and 1. And so you're getting rid of the integer part. And so I originally thought about working with this group all semester instead of this one, since they're isomorphic. But I thought it would be useful to remind ourselves of the things from trigonometry, which is what this one does. So of course it always begs the question, since these two groups are isomorphic, why do we always do trigonometry and precalculus with this one? Why do we measure angles and radians? So it's worth pointing out, this would be measuring angles in what I would call revolutions. So 1 revolution would be 2 pi radians. Well, the reason why has to do with the calculus formulas. If you measure angles and radians, the derivative of sine of theta is exactly cosine of theta. If you measure in revolutions, that's no longer true. So there's our first example. By using a homomorphism and the first isomorphism theorem, we've proven an isomorphism between these two groups. The other examples we're going to do are similar. The next one, we're going to let G be a cyclic group. And I want to show that G, and we're going to assume G has order n. And I want to claim that this group is isomorphic to Z mod NZ. So we've already proven this once, but now I'm going to point out a simpler proof. The simpler proof is to consider the homomorphism from Z to this cyclic group, where we define phi of n to be g to the n. This, I think before I called this the exponential function base g. We already showed previously that this is a homomorphism, and we already showed previously that the kernel was Z mod NZ. Was NZ. So the only thing left to show is that it's surjective. And if I can show that, then if I apply the first isomorphism theorem, I have that the image of phi, which if this is surjective, is all of G, the cyclic group generated by G, is isomorphic to Z mod the kernel of phi, which is NZ. So by doing this approach, I get to skip all that nonsense about homomorphisms being well defined. And that's one of the reasons I like using the isomorphism theorems, is it allows me to prove isomorphisms without having to talk about isomorphisms being well defined. So why is this surjective? I'll just take an equivalence class in Z mod NZ. Oh no, wait, I'm working in G, right? Take any element in the cyclic group generated by G. Then it must be of the form G to the I for some power I. Then clearly the exponential function sub G of I is G to the I, which is X. So there you have it. An alternative proof that every cyclic group is isomorphic to Z mod NZ. Finally, as another common example, one can prove that Sn mod An, this is the symmetric group, so the set of all permutations. On the integers 1 through n. And the other one is the alternating group, so it's just even permutations, which we remember means permutations that can be written as a product of an even number of transpositions. You can prove that this group is isomorphic to Z mod 2Z, this quotient group. How do you do that? Well, you take the signature homomorphism that we've defined previously. Observe that the signature homomorphism of the identity permutation is 1. The signature homomorphism of the permutation 1, 2 is -1. So it's surjective. Oh, sorry, if I remember correctly, I used -1 plus 1, right? We'll stick with that. So it is surjective. So the image of the signature function is -1 plus 1. By the first isomorphism theorem, this is isomorphic to the domain modulo the kernel. And as we've discussed previously, the kernel is the alternating group. And so this is a lot easier than trying to define a direct isomorphism between two different quotient groups in this case. Although here I should note that I don't have Z mod 2Z. What do I need to do next? I need to note that -1 plus 1, this is a cyclic group generated by -1. So that is isomorphic to Z mod 2Z. I could have been using 1 bar, 0 bar, and working mod 2 here. But I always kind of like the -1 to the power calculation instead, because I find that's a little easier to understand instead of working mod 2. So we see if you use the first isomorphism theorem, you can change the problem of finding isomorphisms between groups, where one of the groups is a quotient group, or both groups are quotient groups, with the problem of finding a surjective homomorphism whose kernel is the subgroup you're interested in, that you're quotienting by. Not only that, but if you use this approach, you don't even have to show this kernel is normal, because that comes for free from the first isomorphism theorem.